All right, so let's start our class. As the plan, today we're going to, in the lecture time, we're going to do the lecture, which is new content. And in the lab time, we're going to review the unit 1 parts, okay? Not just the unit 1 exam, okay? So I'm going to give you out the unit 1 exam, okay? So the unit 1, usually most of people perform pretty good. So I'm not going to talk about all the questions in the unit 1, but if you have some single questions, you have a question, then you can talk with me. And then meanwhile, I will give you some unit 1 practice coming from the ACS, American Society of Chemistry, or American Chemistry Society, okay? So that is kind of like a question pretty similar like the final. Okay, so this is our plan. I already print out, so I will give you out in the lab time. So we just do the practice. Just to let you know, most of those are multiple choices, and the unit 1 parts probably is easier. And I think 80% those are all conceptual questions. Okay, we talk about the conceptual, but you need to for some of the readings or wording, maybe you're not familiar. So that's why you need to do those practice and be familiar with how the ACS making those exams. That makes sense, right? All right. So let's start to review a little bit about what we talked about last time. Last time we spent the whole class to talk about how to use the based on the molecular formula, then draw the Lewis structures, right? And we talk about drawing the Lewis structures. For example, if you have the CO, right? So first, what we're gonna do, we need to count how many numbers. Well, this one is not, let's see, SO4, SO4, SO3. This is compound, right? So first of all, you need to know which one is a central atom, which one is a side atoms. So this guy is a central atom because they only has one, is a central. And oxygen here is a side atom because oxygen has a multiple number, so that's a side atom. And then you're making the skeleton for the structure, which is put the central atom in the central and put the side atom on the side. And then you need to count how many valence electrons for those guys. SO3 has how many? So this guy valence electron, not how many electrons. So oxygen and sulfur are all in the S, right? A six group. So this guy has a 6. The time oxygen 6, but we have 3 of oxygen. So you add them together, totally 18 plus 6, that's 24 valence electrons, which means we need to assign 24 dots around it, right? 24 dots around it. And then first of all, you need to put in those 6 dots, 1 pair of dots between each of the elements. And we assume that's a 1 bond shared electrons, right? So they have to have a bond. Then we're going to assign the rest of the dots. We talk about it, we go the central atom first. So we put the 8 of this, and then we go for the rest of this. So we have 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so when we assign 24 dots over here, we shouldn't add no more because the valence electrons limit how many dots we assign. We need to assign 24, so we should only draw 24. But in this case, you will see oxygen, sulfur, they have 8 electrons, which is octet, follow the rule. But this oxygen not follow the rule, which means we have to think about, we short of the dots. We need to think about we have a double bonds or triple bonds. So here, the only thing that you can make in the additional double bonds, which is we're moving those unpaired electrons. And this electron, so not unpaired, the lone pairs. And this lone pair is not shared electrons. we're moving those lone pairs into the shared area. And so in this case, this oxygen and sulfur will have 2 pairs of the shared electrons, and then they're going to making double bonds. So you will see the Lewis structure will be just like this. So that is the Lewis structure for the SO3. That makes sense, right? Yeah. And also we talk about, okay, so how about the ions, the polyatomic ion? Then let's make a very similar one. SO3 is the molecular compound. This guy is neutral. But SO3 2-, this is a polyatomic ion. They have a charge, right? So this is a sulfide. So then what we do? Well, again, we're gonna put the sulfur in the center, oxygen on the side. And then when you count how many valence electrons over here, again, sulfur 6, oxygens have 3 of this, 6 times 3. And don't forget, this guy has a charge. They have a 2 negative charge, which means they need to gain 2 more valence electrons. So you need to add 2 more electrons. Then in this case, it's no more 24 valence electron. They become 26 valence electrons. Then you're going to assign the 26 dots instead of 24. So the structure will be completely different, okay? It's completely different from the original, from the SO3. Then, okay, so we put those dots over here, then we start to assign 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so in this case, once you're assigned 26 dots here, then you realize, whoa, everything is octet. You don't have to making any double bonds or single bond anymore, right? So obviously the oxygen, each of the oxygen has 8, and the sulfur also has 8. So now in this case, you just need to get rid of those shared electrons to making a bonds. Remember, must be shared electrons. And here the sulfur has 1 lone pairs of there, but this one is not shared. So you're going to keep those 2 dots over there. So that is the Lewis structure for SO3 2-. Since this guy is a charge, and don't forget, we need to write a charge over here. And that is the Lewis structure. Have to have the charge over there. If you don't have a charge, then that's completely different. If you don't have a charge, then that's going to be this structure. But since you have 2 additional electrons over there, the Lewis structure will completely change. And just let you know, when we talk about the shape also completely different. Okay, today we're going to talk about a little bit shape. So the shape will also be completely different. Okay, so generally this is what we talked about last time. We also talk about some of the exception, and we talk about some of the compounds like PCl5. PCl5 in the central atom, they have 5 bonds, which means they have 10 electrons. And this is the exception because we talk about all the elements should follow octet, which means 8 electrons. But here this central atom has 10, which means it's not follow the rule, but this is exceptions, right? And we talk about side atoms always follow octet. Okay, side atoms always follow octet. Only the central atom can have a chance to not follow. Okay, can have a chance to not follow. Okay, so so generally this is, we talk about some of the exception. And today we're going to talk about something is also follow the Lewis structures. Okay, yeah. So let's talk about the topic is called the 4 mole charge. Okay, the reason we have the 4 mole charge, before we talk about 4 mole charge, we need to raise a question. Okay, why we need this concept? Okay, so first, I'm going to give you one of the questions, like a structure for CO2. Okay, the Lewis structure for the CO2. So if you draw the CO2, you can draw something like that. You can also draw something like that. Well, if you look at the Lewis structure for both, the carbon has 4 valence electrons, oxygen 6 times 2. So we have totally 16 valence electrons, which means we're going to draw 16 valence electrons over here. But if you look at the both, and then you realize each of them has the 16 dots, including the dots in the bond. And also each of them follow each of the elements, doesn't matter which one, they all follow octet, right? So this one, this oxygen has 80 electrons, right? And this oxygen also has 80 electrons. So this one has 18 electrons, and also each of them follow octet. This guy also doing the same thing. This guy, oxygen octet, carbon octet, and this also octet. But the point is, which one is the correct formula, right? I mean, for the Lewis structure, you cannot have 2 different Lewis structure for only one same compound. It doesn't make sense, right? So that is why we need to using the formal charge concept to figure out which one is the correct formula. Okay, which one is the correct formula? So first, then let's talk about, okay, what exactly is the formal charge? Okay, what exactly the formal charge? Formal charge actually is just give you one of the equation and help you to figure out the charge for each, the formal charge of each of the elements. And we try to making most zeros for the charge. The more zeros that you can find for the formal charge, the better for the element, for the formula it is. Okay, so for example, the formal charge equation is just equal to the number of the valence electrons, the number of the valence electron for the elements, subtract a sum, subtract the sum, subtract the number of the bond, okay, number of the bonds, plus the number of the electrons not in bond. Okay, so this is the equation to figure out the formal charge. Formal charge is a number of the valence electrons subtract the sum of the number of the bonds plus number of the electrons not, sorry, that's not in bond. Okay, number of electrons not in bond. Okay, so this is the way to figure out formal charge. Then let's just do one of the examples. Okay, so let's first figure out the formal charge for each of the oxygen, carbon, and oxygen. Okay, so for this one, oxygen, this oxygen, again, the number of valence electron for oxygen is a 6, right? So this guy is a 6, and then you subtract the sum around the oxygen, how many bonds the oxygen has. Well, if you look at this, how many bonds this oxygen has? They have 3, right? So you need to write the number of the bonds, which means how many bonds this guy has. They have 3, plus number of the electron not in bond. How many electrons this guy do not have, not in the bond? 2, right? So you plus 2. And then you will figure out the formal charge for this oxygen is 6 minus 5, which is plus 1. So the formal charge for the first oxygen on the left, the oxygen on the left is plus 1. Okay, so this guy, the formal charge for this oxygen is plus 1. Okay, then let's see, what is the formal charge for this carbon? Okay, the carbon valence electron is 4. And you subtract the number of the bonds for this carbon, how many bonds they have? They have a 3 here, have a 1 here. So this guy has a 4 bonds. And then the subtract the plus the number of electrons not in bond. Is there any dots, electrons not in the bond for carbon? No. So just plus 0. And then you will see 4 minus 4. So the formal charge for this carbon is 0. It's 0. Okay, the formal charge for this carbon is 0. And then we can do the formal charge for this oxygen again. So the oxygen on the right, valence electron is 6. You subtract the number of the bonds. This guy has 1 bond, so plus 1, plus number of the number of electron not in bonds. This guy has a 6 dots not in the bond, so you plus 6. And you realize it's a 6 subtract 7, which is -1. So the formal charge for this oxygen is -1. Then you will realize this is a +1, is a 0, and the +1. +1, 0, and a -1 for each of this formal charge. Okay, well, it's not, so this is the result for the formal charge for this formula. Then let's look at this one. Okay, yeah, the formal charge is, you will figure out the difference when you compare things. If you just got the formal charge for one formula, it's nothing. Okay, you have to compare the other formula and then you figure out what is the difference. Okay, then let's figure out the formal charge for this compound for each of these elements. The oxygen over here, well, the formal charge and the valence electron for this oxygen is 6, and you subtract the sum of the bond, number of bonds. This guy has 2 bonds, plus number of the electron not in bonds. They have a 4, so plus 4. Then you will see 6 minus 6 is equal to 0. So this guy formal charge is 0. Carbon is doing the same thing. 4 subtract 4 bonds plus no electrons. So 4 minus 4, this guy still equal to 0. And the oxygen on the right side, you will see is a 6 subtract number of bonds plus 2 plus number of electrons, which is 4. And this is also give you 0. So that means this guy has a 0, 0, 0 for all the elements. Then you can tell the difference. This guy has a +1, 0, -1. This guy 0, 0, 0. And which one is a best formula, Lewis structure? The more zeros, the better. Okay, the more zeros, the better. Okay, so that is the conclusion. If you compare the two formulas, this Lewis structure, if you cannot tell the difference, then you figure out the formal charge. The more zeros, the better for the formal charge. Okay, so that is why this is the best Lewis structure. Okay, this is the best Lewis structure for the CO2. Okay, this is the best Lewis structure for CO2. And everything is a 0. And this is the purpose for the formal charge. Okay, that is the purpose for the formal charge. And let's do one of the other one is a complicated one. So let's see the PO4, 3 minus. This is a phosphate. Okay, phosphate ion. You can draw the phosphate ion like this. And that's gonna be the Lewis structure. You can draw it like this, or you can draw something like that. If you count the dots, both of them follow the same dots. If you count 5 plus 6 times 4 and plus 3. So that's 24 plus 8. That's a 32. So both of them have 32 valence electrons. But the point is, which one is a correct formula? Okay, which one is a correct formula? I mean, if we don't talk about the formal charge, and then both of them are correct. But if you talk about the formal charge and there's a one is the correct one. Okay, there's a one is the correct one. Then again, you just need to calculate the formal charge for each of this. And then you will figure out, since those oxygen are all identical, once we figure out the one of the oxygen, the rest of this should be the same, right? Then you see the oxygen over here, that's a 6, subtract 1 bond plus 1, 2, 3, 4, 5, 6, 6. So you got -1. So this oxygen is -1 for formal charge. The rest of the other oxygen are all -1. And then you will see the phosphor inside, that's going to be 5, subtract 4 bonds, and plus no electron. So this is +1. Then this guy is +1. Then you see, okay, all the elements are none of these are 0. They more or less has a number, right? The -1, -1, -1, -1, and this is +1. But if you look at over here, you will see this oxygen is a 6, subtract 2 bonds over here, plus 4 dots. So 6 subtract 6, that's a 0. So this guy is a 0, this guy is 0, and 0, and 0. So all the oxygen are 0, but obviously phosphor is not 0, right? Phosphor is a 5, subtract 8 bonds, and plus no dots. And this guy is -3. So this guy is -3. Well, obviously the phosphor is not follow the octet. You see, this guy has 88 bonds, means they have 18 electrons, 16 electrons. So obviously phosphor is not follow the octet, but this actually is the best Lewis structure for the phosphate, because they have most of those oxygen are 0s. Okay, yeah. So this is why we have that is why we have the what is that called? The formal charge, the concept. So let's take our study guide. There's a question in the last one page. So you turn to the last page. The first question, number 6, okay, page 21st, which is the last page, question number 6, and they give you the 2 formula and try to figure out which one is the best Lewis structure for the compound. So you can go ahead to work on this to figure out which one is the best formula, the Lewis structure for this formula. Just try to figure out the one that has more 0s, then that's it. Try to figure out the one that has more 0s. Okay, so let's come back to look at review this. Okay, the answer is this one, on the one on the right side. Okay, but let's just look at the formal charge again. Formal charge is the number of the valence electrons subtract the number of the bonds plus number of the electron not in the bond. Okay, so for this oxygen, they have a 6 valence electron. Oxygen has 6 valence. Subtract number of the bonds, they have 1 bond plus 6 dots. So this formal charge is -1. So this oxygen is -1. For the hydrogen, then you know is just 1 subtract 1 plus 0. So that's 0. So this hydrogen is 0. Then nitrogen over here is a 5 subtract 4 bonds plus no dots outside and give you as a +1. So this nitrogen is +1. And the oxygen over here is a 6 subtract 2 plus 4. So give you 0. Okay, so now we have 0, 0, +1, -1. But if you look at over here, you will see hydrogen here is 0. Oxygen here is also 0. Nitrogen is 0. This oxygen all zeros. So that is why this is the best one. Well, if you don't do the Lewis structure, there's another way can help you to identify which one is easy. And then that's generally basically is coming from the Lewis structure for their elements. Oxygen, you see, oxygen has 6 electrons, which means they need to pair with 2 other electrons. So the most case they can, so generally if you want them stable, they want to bond the 2 electrons, which means give your 2 bonds. Okay, we talk about shared electrons, 1 pair of shared electrons giving your 1 bond. So this guy need 2 shared electrons, so they should have 2 bonds. So the generally for oxygen, 2 bonds is the most stable form for them. Okay, and then if you look at nitrogen, nitrogen has 5 electrons. So this guy has 3 single electrons. So they would like to pair 3 other electrons. So they should have 3 bonds. Most of the case, okay, either is 3 double bonds, 3 single bonds, or 1 double bonds, 1 single bonds, or 1 triple bonds. So at least they need 3 bonds to make it stable. Does make sense, right? So if you look at here, this nitrogen has 1 single bonds, 1 double bond, but they totally add together, they have 3, right? 3 bonds. And this oxygen has 2 single bonds, but they have 2 bonds. This oxygen has 1 double bonds, still 2 bonds. That makes sense, right? So that's why this guy makes it stable. But if you look at it here, this nitrogen has 4 bonds. So obviously it's not that stable. Okay, so naturally all the elements, they want to make the formula, they try to be stable. That's it. But so that is why if you look at here, that is why the oxygen try to be stable. So they need to have 2 bonds with it. That makes sense, right? Yeah, you see, this oxygen, they want to have 2 bonds with it. Okay, this guy want to have 2 bonds, and the carbon usually would like to have 4 bonds. Okay, carbon would like to have 4 bonds. That makes sense, right? Because a carbon has 4 single dots on the outside, so they would like to have 4 bonds, either 4 single bonds, or 1 double bonds, or 2 double bonds, or 1 triple bonds, 1 single bonds. That's it, right? Yeah. So, but doesn't make they shouldn't have 5 bonds. Okay, for carbon they shouldn't have 5 bonds, or they have 3 bonds. It doesn't make sense. They make it not stable. Okay, are you clear? about what I'm talking about? Okay, so let's take a break and then we will talk something different. Okay. Okay, so let's come back. The next part, we're going to talk about the polarity. The polarity of bond. The polarity of bond. Have you heard of what is the polarity? Well, generally to you, what that mean, polarity? To you, okay, what is the polarity mean?
Positive side and negative side.
Okay, yeah. Then what is the North Pole, South Pole mean? Okay, so polarity in general doesn't matter is something. You may have a North Pole, South Pole, and also you have an equator. So that is the temperature difference. Okay, so polarity in general is a separation between the separation is extreme separated parts. Okay, so North Pole is extreme cold. Let's talk about the temperature difference. Okay, and we also has a magnetic pole, right? North Pole, South Pole, and this is talk about the magnetic difference between. But the polarity over here is talk about the electronic difference. One extremely positive charge, the other side is extremely negative charge. So that is the difference between the polarity. Okay, so that is the polarity. So you can think about why we have the polarity. So in general, so first let's talk about something, the case that's do not have a polarity. Okay, for example, if we have a hydrogen and we have another hydrogen, the hydrogen, they are sharing the electrons. They only have those two electrons. Okay, so in these cases, both of the hydrogen actually they are the hydrogen, the electrons in the middle is not a statically sitting there. They're going to move around. They're going to move around. And then actually the two hydrogen is constantly pulling the electrons to both sides, to each side. But the point is they're doing the tug of war, but the muscle of those hydrogens are the same. So it doesn't matter how they pull, they pull exactly the same. So the flag in the middle, they always in the middle, right? The electrons is not moving to one side. They're not going to move in two sides. So that means the charge effect, they're 50-50 50% share the electrons. The electrons is not close to any of this. They are not going to close on that. So there, the electron is evenly distributed to each ions, each of the atoms. Then they're not going to have a polarity. They're not going to have the polarity. The polarity is coming out when the electron sharing of the electrons is not going to even. Okay, the electron, the polarity is coming out when the electron is not going to share evenly. Okay, it's not going to share evenly. So that is the why we have the polarity come out. Give you one example is like a hydrogen and fluorine. So we know the fluorine has 7 electrons, and the hydrogen, originally at the beginning, they made a deal. So they're going to share the electrons. But the point is fluorine, and we talk about the electron negativity. Electron negativity is talking about they're going to show the muscle who can able to pull the electrons towards it, right? And we talk about on the top right parts, this guy has really strong electron activity, like fluorine. Fluorine, they has a strong muscle to pull in the electrons. During the tackle wall to pull in the electrons, they're going to pull the electrons more close to it. Yeah. So now the electrons is not going to in the middle. Instead, they're going to really close to the fluorine. But the point is, this electrons still has a partial that it belong to hydrogen. Although it's not 50% sharing, maybe they go 90-10 sharing. But again, it's not completely, the fluorine here is not completely gain the electrons, right? We still have a little bit of sharing with the hydrogen. So this is very important. So in this case, but the point is, those electrons is more close to the fluorine, so make the fluorine has a more effect on the negative charge. Well, if the fluorine completely gain the electron, then the fluorine will be a 1 positive charge. That makes sense, right? But in this here, since the electron is not completely gained by the fluorine, but it's close to here, there, so maybe the fluorine gain 0.8. The gain the negative 0.8 charge, not completely 0.1 negative 1 charge, but they got 0.8. I don't know. This is just my guess, but are you clear about? But in this case, well, hydrogen is not completely losing the electrons, but they may got a 0.8 positive charge because the electrons is more close. This guy still not completely losing the electron to got a completely positive 1 charge, but they have a partial charge of there. Okay, that makes sense, right? So you will see we got a trend over here. We got a trend here. So on the fluorine side, we have a partial negative charge. This is called a partial negative. This guy is a partial negative, but for the hydrogen side, they have a partial positive. Partial negative and a partial positive. So now the polarity is coming out. One has a positive charge, one has a positive negative charge, and then we got 2 poles. One is a positive polar, the other is the negative polar. Okay, so that is why we call this is polarity. Okay, but for this hydrogen, then there's no polarity. So we call this guy as a non-polar. Okay, so the bonds shows over here. Since this bonds shows over here, we call this non-polar bond. but the bonds between hydrogen and fluorine here, and we call this is a polar bond. Non-polar bond and the polar bond. But just to let you know, okay, even the polar bond is still weaker than polar bond is still weaker than the ionic bond. It's still weaker than the ionic bond. It's because, I mean, ionic bond is completely gain or lose electrons, but this guy is still partially gain or lose electrons. So it's still weaker, but those are the two different situations for the molecular compound, okay? So generally, the nonpolar and the polar bond still belong to covalent bond, which means it's still a molecular compound. Okay, those still belong to covalent bond, nonpolar and the polar bond. Okay, yeah, nonpolar and a polar bond. Are you clear? Okay, so here it is telling you why we have a polar molecule, well, why we have a polar bond, why we have a nonpolar bond. Okay, once they have a polar bond, actually this trend we talk, see, we write an arrow here. So this has a trend, and this trend we call this is the it's a special name. It's called the dipole moment. It's called the dipole moment. The given name is called a dipole moment. So dipole moment, if we talk about which one has a dipole, which bond has a dipole moment, in general, it's just talk about which bond is a polar bond. Okay, yeah, which bond has a dipole moment, generally is to talk about which bond is a polar bond. That's it. Okay, so we just gave it its name. It's called a dipole moment. So this trend is called a dipole moment. Okay, so once this guy has a dipole moment, then definitely it's a polar bond. For the nonpolar bond, they don't have a dipole moment. Okay, these are 50-50% shared electrons. Okay, yeah. So now it's telling you the difference between nonpolar and a polar bond. All right, but the point is, how can you determine which one is the polar bond, which one is a nonpolar bond? You don't know, right? Yeah. So you cannot tell which one is a polar and a nonpolar. But here we're not going to talk about the major difference. I'm just give you the rough idea. It's just to try to we need to try to find the difference. Try to find the difference of the electron activity of two elements. Then you will figure out whether this is nonpolar or polar bonds. So for example, the electron activity, I'm going to just write the electron activity for chlorine, that is a 3.0. They have a number. The people gave us a number. For carbon, then that's a 2.55. For the hydrogen, is a 2.20. Okay, 2.20. So now you will see. Okay, now if we have two chlorine gases, with this guy making a molecule, and what is the bond in between over here? Then what you need to do, you just need to try to figure out the difference of the electron activity. Since the chlorine 3.1 on the left side is a 3.0, And the right side is also 3.0. So difference is 0. So the electron negativity, the difference of that is 0. That means this guy has a nonpolar. It's a no. This guy is a nonpolar. Which means if you're in the future, if you see the bond between the both sides are exactly the same elements, so for sure this bond is a nonpolar bond. Okay, for sure that's a nonpolar bond. And well, then you will see, okay, so how about the carbon and the hydrogen bond? The difference over here, carbon is 2.55, subtract the hydrogen 2.20, and the difference over here, it gives us is 2.35. Well, 0.35 is still belong to nonpolar. I'm going to tell you why. So the general rule, I'm going to write a rule over here. So the difference of the electron activity, if this is a smaller than 0.4, then we just assume if the difference of electron activity is smaller than 0.4, we assume this guy is a nonpolar. They are having a nonpolar bond. Okay, so the difference of the electron activity is less than 0.4. We assume that's nonpolar. But in between 0.4 to 2, and we assume that's a polar molecule. This is a polar bond. But if it's larger than 2, we assume this is ionic bond. Okay, so if it's larger than 2, we assume this is an ionic bond. So in this case, you will see ionic bond actually is an extreme polar bond. It's even bigger, it's even polar than the polar bond. Even more polar than the polar bond. That makes sense, right? Yeah. So this is the difference. So that's why if you're talking about the carbon and the chlorine bond, then you will calculate, okay, so the electron activity over here is a 3.0 subtract 2.55, and then that's a 0.45. So we assume that's going to be a polar bond. This bond will be a polar bond because it's larger than 0.4. Although it's just a little bit hard, but it will be larger. And then you will say, okay, how about the hydrogen and the chlorine bond? Hydrogen and chlorine bond. And the difference of the electron activity, that's just 3.0 subtract 2.20. And then you will see, okay, so this is 0.8. So for sure, this is a polar bond. Okay, for sure, this is a polar bond. That makes sense? Okay, so this is generally, this is I mean, numerically to figure out whether this bond is a polar and a non-polar. But the point is, okay, the reason I'm just go through this very quickly is because this is nonsense for our exam. Because you're not going to give in the numbers of the electron activity. How come you figure out whether this is polar or non-polar? But there's another way to test, which is making the comparison. Okay, for example, so we have a carbon and chlorine bond and a carbon fluorine bond. So now we have those two bonds, and we can, based on this, the definition to determine which bond is more polar. Which bond is more polar? Well, then we know we need to figure out the difference of the electron activity. And did you remember the trends for the electron activity? We have a two parts trends, right? On the top to the bottom, the electron activity is from high to low. From the right to the left is also from high to low. Now, which means the fluorine is sitting over here, chlorine is sitting over here, and the carbon is sitting over here. then you just need to look at the difference between the two. So now, so if you want to figure out the difference, okay, fluorine definitely has a higher electronegativity than the chlorine. Carbon is not changing. Okay, so then tell me which number will be higher, fluorine minus carbon or chlorine minus carbon? Then you can think about fluorine is higher than the chlorine. So the difference, if you say fluorine subtract the carbon and the chlorine subtract carbon, which one is higher? What do you think? Obviously it's fluorine, right? So that is why this guy is more polar. So carbon and fluorine bond is more polar than the carbon chlorine bond. Okay, so this guy is more polar than the carbon chlorine bond. That makes sense, right? So you can base on generally you can base on the trends to figure out which bond is more polar. Okay, so that's why we have some practice shows in the study guide, and we can look at it on the page 17. Page 17. On the page 17, okay, so you can see carbon and a carbon bond. Question number 4, carbon-carbon bond and a carbon-hydrogen bond. Here talk about which one is the most polar bond. Carbon-carbon bond and a carbon-hydrogen bond. So obviously it's a carbon-hydrogen bond because carbon-carbon is both are the same. So the difference is 0. But the carbon-hydrogen, at least those are the different, not the same elements, right? So they always has some difference. So definitely carbon-hydrogen bond is more polar than the carbon-carbon bond. That makes sense, right? Yeah. And then let's see the nitrogen-hydrogen bond and oxygen-hydrogen bond. Then again, you're gonna have your periodic table with you. Hydrogen is over here. Oxygen and the nitrogen, oxygen is here. Nitrogen is over here. Then if you want to see the difference, okay, which one is far away? Oxygen and hydrogen or nitrogen and hydrogen, which one is more far away? Oxygen is more far away. So we talk about difference, right? The longer, the more far away, the more difference it will be. That makes sense, right? Because we talk about this area is the highest. Okay, this area is the highest. So obviously, this oxygen and hydrogen bond has a more polar than the nitrogen hydrogen bond. Okay, so then again, hydrogen and the fluorine bond and hydrogen and the chlorine bond. Okay, again, hydrogen is over here. I think we talk about this, right? Similar, it's similar like a carbon chlorine bond and carbon fluorine. Fluorine is over here. Chlorine is over here. Okay, fluorine is stronger than chlorine. So you see the difference between hydrogen and fluorine should be bigger than the chlorine and hydrogen, right? Because fluorine is a bigger, has a bigger electronegativity than the chlorine. So that's why the fluorine should be bigger than the chlorine. So that's why this guy should have the higher, more polar than the other one. Okay, then you can look at how about the next one, nitrogen and oxygen, carbon and oxygen. So which one? Look at your periodic table. Oxygen is over here. Nitrogen is over here, carbon is over here. Then you can see what is the difference. So obviously those two difference is bigger than this two species difference. That makes sense, right? Yeah. So carbon oxygen should has the bigger higher polar, is more polar than nitrogen oxygen, because nitrogen oxygen, those two are closer. Make sense? Okay, yeah. So this guy should be stronger than that. Okay, so now go ahead to work on the rest of this. How about the sulfur hydrogen and the oxygen hydrogen? And the PCl, SCl, CH, and the NH. So you can go ahead to look at the difference between those two. Which one is more polar? Just based on the periodic table. That's it. Okay, so now you can see first one, sulfur hydrogen, oxygen hydrogen. So sulfur is over here, oxygen is over here. Oxygen is stronger than sulfur. Okay, so hydrogen is off here. Then if you see the difference between sulfur and hydrogen should be weaker than oxygen and hydrogen, because oxygen has higher numbers. Okay, it's bigger than sulfur. So the hydrogen oxygen should be bigger than sulfur hydrogen. Okay, next one, phosphor and the chlorine. Chlorine is over here. Okay, phosphor and chlorine, sulfur and chlorine, those are in the same level, same period. So definitely phosphor and chlorine has a bigger difference than the sulfur chlorine. So this guy is stronger. The next one, carbon hydrogen, nitrogen hydrogen. Those are almost in the same level. So carbon hydrogen is smaller and the nitrogen hydrogen is bigger, right? So this guy is also, nitrogen hydrogen is bigger. And just to let you know, carbon hydrogen, we just based on the calculation, we talk about this guy is a non-polar. This guy is non-polar, but the nitrogen hydrogen is a polar bond. So you see, you can tell this polar bond definitely is more polar than non-polar bond. Okay, yeah. So here, this is the things that I hope you can help you to understand the difference. You don't have to directly figure out whether this compound, and those are polar molecule or non-polar, but at least based on the comparison, you can figure out whether which one is more polar than the other. Make sense? Okay, yeah, so let's take a break and then we will talk about the last concept for today, which is the geometry or the shape of the molecule. Okay. Okay, so let's come back. So we're going to next part, we're going to talk about the shape of the molecules or the geometry of the molecules. Okay, the reason those guys has a shape, the molecule has a shape, they have a purpose. That's because of the electron space. Okay, electrons, electron cloud. And the following parts, we're going to talk about the one of the model. The model is called the VSEPR model. And VSEPR means valence shell electron pair repulsion. Okay, so VSEPR, valence shell electron pair repulsion. Okay, so the reason you can think about the reason the molecules has a shape is because some of the molecule, for example, like water molecules. So let's say the water. The Lewis structure for the water is like this. In this case, you will see the oxygen, the central atom oxygen, actually they combining some of the stuff. They have two of the hydrogen bonds, and those bonds is a valence electron shell. They are combining with another molecules. So this area, so you can think about the molecule, the oxygen atom is like a ball. And the ball has a certain area space, right? If the sum of the certain area space is being occupied and by some other atoms or the electrons, this space will be occupied. And the sum of the space will occupied by the other stuff. For example, here, the oxygen over here, they occupied by these two hydrogen atoms. And also the other two area is occupied by the lone pairs. We're just drawing two dots for the electron pair. It doesn't mean they're not occupied space. They even occupy the bigger space than the hydrogen atoms. Okay, yeah, those two electrons even occupy even bigger space. So the ball of the atoms is very limited. But when the space is being occupied, each of those shells and electron pair will be repelled to each other's. So they more or less will fix to a certain shape. Okay, yeah, so that is why the molecule has a different shape. It's because those guys is repelled to each other. That is why, okay, they repel to each other's. So here, let me just show you one of the demo and for the repulsion. Okay.
Today we will talk about valence shell electron pair repulsion theory, VSEPR. In today's visualization, you have to think of electron pairs as balloons. So imagine that we have some atom in the center here and we have electron pairs around it. VSEPR tells us that the electron pairs will try to get as far away from each other as possible. And so we can use these balloons to figure out what those shapes would be. So some atoms and molecules have two electron pairs around the center atom. And if we tie then two balloons together and look what shape those make, we can see that they make a straight line or right across from each other, 180-degree bonding. However, if we take three pairs, three balloons, and tie them together, you can see that this is the arrangement that we get. I'm not making them into that. That's just kind of the natural lowest energy state that they can go into. So in this, you have, imagine that the atom is at the center. You have these are electron pairs around it, and you have 120-degree bond angles, and it's flat. This structure, the last one is called linear. This structure is called trigonal because it's got 3 sides, but planar because it's flat. Trigonal planar. If we then go ahead and throw a 4th pair on there, not easy to do. So we can see that they take this sort of almost like a tripod arrangement where you have each of the pairs is sort of, look at these real closely, these balloons are not flat, they're pointing down a little bit. Down, 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 just a little bit. And this one's going straight up over the top. This is called a tetrahedral. Named so because it has 4 faces, tetra, 4, hedra, face. Faces, I guess. Tetrahedron is the singular. So you have 1 face, you have like a, think of it kind of like a pyramid. I don't want to say that too much because there are other things we call pyramids. This is the tetrahedron. But you have 4 faces, you have a face here, 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 and on the bottom. The bond angle here, bond angles here are not easy to necessarily visualize, but you can tell that they're more than 90 degrees, but not as much as 120. It turns out that the number is 109.5. And so those are the basic arrangements for electron pairs around the central atom. Chem 1 for 2, 3, and 4 pairs.
Okay, so generally this is the nature. I mean, why we talk about the shape? It's because those shape is nature. Okay, yeah, that because of the electrons is pushing to each other's, they have to form this kind of. So you can think about if we have 2 of those electrons, 2 objects, they're going to naturally become a bond, single, a straight line. But if you have 3 of those, they have to form those triangle things, and we call this a trigonal planar. But if you have 4 of them, then they have to form this tetrahedral form. And I mean, later we will talk about they have 2 other kind. I mean, it's even more complicated than this. They have 5 different stuff, 5 balloons or here, or 6 balloon. And 6 balloon is the maximum that you can put over there. Okay, but majorly we're going to talk about just 2, 3, 4 over there. Okay, so now remember those balloons, and we call those balloons has a special name. Okay, we call those as balloon as a special name. The name is called electron domain. It's called the electron domain. Okay. Okay, remember the electron domain over here actually is just the balloons that you saw. I mean, those electron domain is try to pushing the other domains to each others. Okay, yeah, and the electron domain, the reason called domain is because they occupy the space. Okay, the electron domain, they occupy the space. So for the electron domain, there's a different things can be the electron domain. For example, if you see the oxygen over here, they have 4 different electron domains over here. You see, for oxygen, they have 4 different domains. The lone pair can be the electron domain. The electron lone pair, this guy can be the electron domain. This is one kind of the electron domain. So this guy has one of the electron, one of the lone pair over here, and this guy occupy the whole electron domain over here. And then we have another electron lone pairs. So this guy also occupy another domain. Okay, and somewhat others can also be a long electron domain, which is the single bond. So if you see a compound has a single bond, and the single bond can also be the one of the electron domain. For example, this oxygen, they have 2 of the single bonds shows over here, and this single bonds also be one of the electron domain. Okay, so this guy has a 2 single bonds, so they have a 2 electron domain plus 2 lone pairs. So totally oxygen in the central oxygen, they have a 4 electron domain over here. It makes sense, right? This guy has a 4 electron domain. So in general, this guy should form the tetrahedral form. Based on 4 electron domain, they should form the 4 electron domain for the tetrahedral shape. Okay, this is a electron domain, but not just a single bond. If you have a double bond, double bond can also be the electron domain. For example, the carbon, the dioxide, carbon dioxide. This carbon, you see, for the central atom carbon, they have 2 double bonds, and each of the double bonds is referred to one of the electron domain. So in this case, this carbon actually has a 2 electron domain, and then it turns out it will just the structure you will see is a structure something like that. They have a 2 boron. The carbon is in the central, and the oxygen is on the side. This is carbon, and they have 2 domains like this. So the CO2 actually is a flat, is a line, is a line shape. Okay, so double bonds can also count as 1 electron domain. Most of the case, people got a misunderstanding is the double bonds means a 2 electron domain. No, 1 double bonds is just 1 electron domain, not count 2 electron domains. Okay, yeah, not count 2 electron. 1 double bond is just 1 electron domain. Okay, and the same thing for triple bonds. The triple bond also count 1 electron domain. So triple bonds also count 1 electron domain. For example, there's there's one compound like this. If you're talking about this is the ethene. This is alkyne. This is alkyne. So the carbon, for this carbon, they have 1 single bonds, which is 1 electron domain. And they also has 1 triple bonds. This is also 1 electron domain. So for the carbon over here, the central carbon over here, the shape is a straight line. They only have 2 electron domains. Okay, yeah, they only count the electron. So very, very important. 1 double bonds count 1 electron domain. 1 triple bonds also count 1 electron domain. Okay, yeah, the triple bonds and double bonds, they aggregate together, and then they occupy the same space area. Okay, they occupy the same space area, just like the single bond and the lone pair. That makes sense? Okay, yeah. So in this case, if you're clear about the electron domain, then that's gonna be easier. If this molecule has a 2 electron domain, then what's the shape? If this guy has a 2 electron domain, and then the electron domain generally we talk about the central atom. If you look at the central atom, how many electron domain for the central atom? If they have a 2 electron domain, then they're just going to be a straight line, something like that. Okay, yeah, straight line like this, and we call this shape is a linear shape. This is a linear shape. Okay, it's a linear shape. I can give you another demo. So here, this is one of the demos. If you look at the electron domain, that is just a linear. So have a central atom, you have 2 of the atoms like this. That's okay. But if you have one of the 2 bonds, you see, if you have a double bonds over here, this is also count 1 electron domain. Then those are still a linear shape. That makes sense, right? And if you're talking about, okay, so here we have 1 of the lone pair. This big is a lone pair. The lone pair, the other side is double bonds. This guy is still a linear shape. Okay, still a linear shape. So this is just, once you have a 2 electron domain, then they're going to become a linear shape for the electron domain, okay? And if you have a 3 electron domain, then that's going to be a triangle over here. And this is what we call the trigonal planar. Okay, this is called the trigonal planar. Trigonal, this is called a trigonal planar. Okay, so 3 electron domain is just like this. If you have a 1 single bonds, then you will see, okay, so this is a trigonal planar. It's called a trigonal planar. They have a 3 side domains, and those are repulse to each others, and then they are naturally become a trigonal planar shape. And then the reason they are said they have a 3 side, and then if you look at this, there's a flat. So that's called a trigonal and a planar. Okay, trigonal planar. But if you have a 3 electron domain, then this guy is complicated. It's not a 2D anymore. It's become a 3D shape. Okay, the 3D shape is hard to draw. And usually we're using wedge and a dash to draw the 3D structures. The wedge is talk about the bond is a stack out from the flat, from the 2D. The dash is talk about the one is stack in. Okay, so wedge and a dash structure. This generally this is what we talk about. Wedge and dash. You will not see this until you're taking the organic chemistry. Okay, you will not see this until you're taking the organic chemistry. Then the teacher will want you to draw the 3D structure for the molecules. Okay. All right. So this one we give its name is called the tetrahedral. Yeah. Oh, yeah. This guy is a 4 electron domains. You have a 4 electron domain, then we give it tetrahedral. Tetra, that's a 4. Hedral, that's face. Okay, tetrahedral, that's a 4 face. This guy will generate 4 faces. So if you have one more bonds over here, so maybe the bonds, 4 bonds is easier. 4 bonds is easier to see. You see, this guy has 4 bonds, right? And they have 4 bonds. And this is a 3D. Each of the bond angle, we can show the bond angle here. The bond angle between each of the bonds should be 109.5. Okay, but if you're talking about the bond angle between this, the bond angle is 180. There's a bond angle. And the trigonal planar, that's just 120 bond angle. And the tetrahedral is a 109.5 bond angle. Okay, yeah. So those are the bond angle to each others. And if you look at the trigonal planar, you see the bond angle is identical for each of the bonds. It's just 120. Okay, the 360 you divide by 3, then you got 120. Bond angles. And for the flat one, then you will see the bond angle is just 180. Okay, because that's a flat, it's a linear shape. That makes sense, right? Okay, yeah. So far we're going to talk about this for today, and obviously the shape and geometry we haven't finished that yet. Okay, we'll continue talk in the next class. Okay, in the next class. Okay, so let's take a break, and then I'm going to give you the unit 1 exam and also the practice. Okay, yeah. You have a question, Melody? Yes, we are going to the lab. Yeah, we have other class here.